This is the second part of section 12.5 on the chain rule. And we are looking here in example 5 at, I'm going to say it's sort of an application problem of this chain rule stuff. I'm not sure if it's an application you're going to care too much about, but hey, it's something I could find that works. We're talking about the surface area in square meters of the human body. So basically, kind of like how much skin do you have? It can be approximated using this equation. S, the surface area, is 1/60th times the square root of HW, where your height is given in centimeters and weight in kilograms. Child is 125 centimeters tall and weighs 34 kilograms, currently growing at the rate of 3 centimeters per year and gaining 2 kilograms per year. Find the rate of change in the surface area. So let's see. We can definitely see that S depends on H and W. If I start my chain rule diagram here. And then both the height and weight are changing with time, right? That's per year. So H depends on T. W also depends on T. So I could say then the rate of change of surface area, ds dt, would be the partial derivative of S with respect to H times dH dt plus this other branch, partial derivative of S with respect to W times dW dt. All right, so let's go ahead and do some derivatives. By the way, in thinking about this S, to make the differentiation process a little bit easier, I'm going to rewrite that as 1/60th, and then I'm going to say H to the 1/2, W to the 1/2. Not only does it get rid of the square root, but it also just gets the HW combination out from under there, so I don't have old-fashioned chain rules coming in as well. All right, so ds dh, I'd have that was a 1/60th, sorry. So I'd have 1/60th times 1/2 h to the negative 1/2 times w to the 1/2, and then that gets multiplied by dH dt. I have something very similar over here. The derivative of S with respect to W. I've got that 1/60th h to the 1/2 times 1/2 W to the negative 1/2. And then I've got the times dW dt. All right, I'm going to just sort of clean that up a little bit before I start plugging in numbers. Let's see. I would have the square root of W on top and 120 square root H on the bottom. dH dt. Over here again, same idea. I would have the square root of H on top and a 120 square root W on the bottom. And that's times dW dt. All right, beyond that, really, I just have to go ahead and plug in numbers. We know H here is 125. W is 34. Growing 3 centimeters per year, so that's going to be dH dt. And the change in weight, dW dt, is that 2 kilograms per year. So I just plug it all in. 34 for W, 125 for H, times the dH dt, which is 3. And the second one, square root of H, square root of 125, over 120 square root of W, which was 34. And that's times the dW dt. which is 2. And you're just going to grab your calculation device and figure out what that is. When I did all of that, I got about 0.045. And really small number, but hopefully it kind of makes sense that it should be. The surface area is being measured in square meters. A square meter is a lot of area, right, when you're thinking about your skin. So the surface area of this child's body is increasing at the rate of 0.045 square meters per year. All right, the last piece of this section has to do with a shortcut for implicit derivatives. You may or may not remember implicit differentiation from Calc 1. It's something that you probably didn't use a ton in Calc 2, so I want to just start by reviewing that process. I'm going to kind of remind you of how you did these things in Calc 1, and then we're going to see that now that we have some new skills, we have a really nice shortcut that we can develop using our Calc 3 methods. So first of all, what was an implicit derivative? Basically, it's when you want to take a derivative, but the function's not solved for y. So in this case, you can see that the equation over here that I have is not solved for y, and in fact, with both a y squared and a y to the 5th in there, there's no way algebraically that I'm ever going to solve that for y. So I'd still like to find that derivative, and again, I'm going to start by just using my old Calc 1 methods. What we do is we say, let's go ahead and take the derivative with respect to x of the entire equation, both sides. All right, starts out simple enough, 3x squared. But right here, I have to treat this as a product. 3x times y squared. And so I'm going to get the first 3x times the derivative of the second, 2y dy dx. Because I'm differentiating with respect to x, not y, keep in mind that y is some function of x, so my chain rule tags on that little extra dy dx piece. Plus, second half of the product rule, the derivative of the first would just be 3 times the second, which is y squared. So a little product rule right in there. And then this last term, minus 5y to the 4th. But again, y is a function of x, so the chain rule tells me I have to multiply by dy dx. And that's equal to the derivative of 0, which is still 0. All right, I'm going to do a couple of things here. I'm going to clean this up just a tiny bit. There's not a lot to do, just multiplication here. And I'm going to keep the two terms that have dy dx in them on the left side, and then I'm going to take the two terms that don't have dy dx, and I'm going to move those to the right-hand side. So I would have 6xy dy dx minus 5y to the 4th dy dx. And on the other side, I'll have negative 3x squared and negative 3y squared. Okay. My goal is to find or solve for dy dx. So I'm now going to factor the dy dx out over here on the left. And then finally I can get dy dx by dividing. Like so. Not a horrible process, although you do have to kind of remember about the product rules and the little extra chain rule pieces in there, and then there's a bit of algebra to deal with. It ultimately took me, about 4 or 5 steps to go through the whole process. Using techniques that we now know in Calc 3, we're actually going to be able to go from the original equation to the final answer in one single step. So keep this answer in mind. Again, hopefully this process looked familiar from Calc 1. And we're now going to look at how to do this now that we know how to do partial derivatives. And so we can get that same answer a lot faster. So first of all, how am I going to do it? All right, well, I'm going to treat the left side of my equation as a multivariable function. So this now, if I just think of this as some function, f of x and y, then my equation was f of x and y is equal to 0. Okay? You really want to start with f of x and y equal to 0, or at least equal to a constant, in order to use this technique. Of course, it's really easy to get that algebraically. Just move all the terms to one side. All right, so I've now got f that depends on both x and y. It looks a little weird to say this, but x depends on itself, right? X still depends on x. And we're treating y as a function of x as well. So y also depends on x. So I could say that if I want to take the derivative of capital F with respect to x, I can use my chain rule and follow these two branches. So let's see. I'm going to go ahead and take the derivative of both sides with respect to x again. Derivative of both sides. And that derivative, based on my chain rule, is partial of f with respect to x times dx dx. Of course, the derivative of x with respect to x is just 1, so that'll be easy in the next step. Plus partial of f with respect to y times dy dx. And that is equal to the derivative of 0, which is still 0. You really want that 0 over there, which is why I say it's nice to start with 0 or at least a constant on that side, because I really want that derivative to turn out to be 0. All right, so let's see. Since dx dx is actually 1, and my goal is to solve for dy dx, I would have, I move this to the other side, partial of f partial of y times dy dx equals minus partial f partial x. And I'm just going to write this in the slightly shorthand notation here. Sometimes we call this f subscript y, right? Times dy dx equals minus partial of f with respect to x. I'm just going to use that notation. Kind of cleans up my formula here. And so I get dy dx is minus f with respect to x divided by the derivative of f with respect to y. That is basically a shortcut for implicit derivatives. Keep in mind one more time, I know I'm harping on this, but it is important. This formula works as long as you started out with some multivariable function equal to a constant. All right, we're going to go ahead and use that. And I'm now going to redo the same problem that I just did in example 6 before, so I'm now revisiting that example. And we're going to go ahead and do it using this nice shortcut. We're going to say, well, this is my capital F. It's already equal to a constant, so no worries there. And according to this nice formula, I now can say that dy dx is minus, and then I have the partial derivative of f with respect to x, That would be 3x squared plus 3y squared minus 0 with respect to x there. And in the denominator, I have the derivative of f with respect to y would be 0 plus 6xy to the first minus 5y to the fourth. Now, algebraically, I can clean that up a little bit, but I think you'll notice already this is really the same answer as we got before, right? Clearly, I can go ahead and distribute the negative sign if I want to, and I can ignore the zeros, which probably when you do this for real, you wouldn't have written in the first place. And there's that answer. All right, so a really nice shortcut for partial derivatives, or excuse me, for implicit derivatives, now that we know how to do partial derivatives. And that brings us to the end of section 12.5.